In section 9.4, we're going to look at the direct comparison test to see if a series is convergent or divergent. And I'm going to recommend right here that maybe you pause the video, turn to page 624, and right underneath the words direct comparison test, you're going to see 3 examples. You might want to read through that opening paragraph above that and look at the 3 examples too. So the last sentence in that paragraph says that of the 2 series that you can see side by side, the second series cannot be tested by the same convergence test as the first series, even though it is similar. All right, so let's take a look at this test for convergence or divergence. Direct comparison test, sometimes known as the DCT, that's how I will abbreviate, and it's totally acceptable. Okay, so the DCT, the direct comparison test. And just a side note here, this test is for positive term series, so it doesn't work for negative terms. So you might want to put yourself a note for positive terms only. Alright, it says let 0 be less than a sub n, less than or equal to b sub n for all n. If the series given by b sub n converges, okay, then this test says that if b sub n converges and b is going to be larger than a, if b is already converging and a is a smaller series, okay, then it must also converge. So when we compare 2 series, we're going to name one a sub n and one b sub n, or anything you choose, but that's just common practice to call them a and b. Alright, so if b sub n converges, and it's the larger one, then this series must converge. It's smaller than the b sub n. So I'm just going to put a note to myself that this is the smaller, okay, the smaller series. Okay, then what about this? What if we said that the series a sub n diverges? Well, if one particular series diverges, then the series given by b sub n, okay, is going to diverge. It's the larger series. So think about the comparison up here. Okay, if a sub n diverges, then b sub n, which is bigger than a sub n, must also diverge. So we're going to look at a couple of examples of using this test. Okay, so here we have a series, and we want to determine if it converges or diverges. So it might take, some time to kind of look at it and analyze it and go, you know what, I'm trying to figure out what it resembles. What's the series that I'm familiar with that it resembles? It looks to me like, if I forget about the +2 for just a second, and I'm going to put myself a note, and I encourage you to do the same, that this series resembles this series right here. 1 over 3 to the n. Because all I'm doing is adding a 2 to the denominator. Well, when I look at this series right here, okay, it's a geometric series. And remember, you can rewrite it as 1/3 to the n. Okay, and it's going to actually be a convergent geometric series with a common ratio of 1/3. So I just put a note to myself, okay, that this series resembles this convergent geometric series. So you always want to kind of state what you're comparing it to. With common ratio, not p, common ratio r equals 1/3. Okay, so we've established a series that we want to compare it to. So the next thing is to think about, okay, which one's a sub n and which one's b sub n? Well, if this series converges, then the one that I'm interested in, okay, should be smaller, okay, than this series right here. Because if this series is smaller than this convergent series, and it's less than it, then it's also going to converge. I wouldn't want to establish that, this is going to be larger than this convergent one, because if this is a larger series, than this one that converges, I have no idea if it converges or diverges. I want to kind of squeeze this series underneath this one. Okay? So how do we go about proving that? Well, we're going to do term-by-term comparison. So let's do a little bit of work over here first. Okay? I'm going to let A sub n equal my given series. Okay, and I want it to be the smaller one. Remember, A is smaller than B. So I want this one right here that I'm looking for convergence or divergence to be smaller than the one it resembles. Since this one converges, I want to force this one to be smaller than this one. So now that we know that A sub n is equal to 1 over 2 plus 3 to the n, okay, the smaller one, then we're going to let B sub n be the one that it resembles. And it won't always be in that order. It just depends upon how we're comparing. So 1 over 3 to the n. Okay, so how do we go from here? Well, we do term-by-term comparison. So I'm going to come down here and say A sub n is equal to 1 over 2 plus 3 to the n. And I want that one to be smaller than or equal to, and I'm going to put a question mark here because I don't know yet until I compare the terms of the series if it is indeed smaller. Okay, so, and then I want that to be smaller than the 1 over 3 to the n, which is my B sub n. Okay, so this one's supposed to be the smaller one, this is supposed to be the larger one. Let's just crank out a few terms and compare them and see what happens. Okay, so it says what? N can be 1, so let's start with 1. So in this first series right down here, just down below, if n is 1, I'm going to have the first term is 1/5. If n is 2, that's 9, that's 11, this becomes 1/11. Let's do about 3 terms. Hopefully that'll be enough. Okay, so n is 1, 2, 3. Now I'm at 3. This is 27 plus 2 is 29. Okay. So I'm going to go ahead and put my less than or equal to with another question mark here because I'm just still yet trying to determine. So now coming over here, let n be 1, we have a third. Then if n is 2, we have a ninth. If n is 3, we have 1/27th. Okay, and so let's just start comparing 1/5 compared to 1/3. Yep, 1/5 is less than 1/3. 1/11th, is it less than 1/9? Yep. And 1/29th is less than 1/27th. Okay, so the larger the denominator, the smaller the number. So this is in fact true. So I've shown by term-by-term comparison that I can remove the question mark here. Okay, so it would be a good thing to come over here and state what you found. So therefore, by the DCT, the given series is going to converge because it's smaller than one that does. All right, let's take a look at example 2. All right, let's determine the convergence or divergence of this series. You might want to go through your checklist. This is not geometric. The limit of the nth term would give us 0. This would not be easy to integrate, so I wouldn't want to use the integral test. So it looks similar to another series, a P series, so let's just kind of start there and see what happens. So we're going to say that this series resembles this series right here. 1 over the square root of n. Because I know how to handle that. That's 1 over n to the 1/2, and that diverges. So we're going to start with that. This is a divergent P series. Okay, so let's figure out which one has to be A and which one has to be B. Well, if this one diverges, then we would want this one to be larger than this one that diverges because it forces this one to diverge if it's larger. I wouldn't want to call this one the smaller series Because if it's smaller than a divergent series, I mean, I don't know, it could diverge or it could converge. All right, so if this diverges, we want this one to be the smaller one, and this series right here to be the larger one. So now let's let a sub n equal 1 over square root of n. Then b sub n is going to be the given series. So that's a little bit different than the last example. So I'm going to put a question mark here. I want this series to be less than this series right here. And we're going to have to do some term-by-term comparison. So let's see what happens. Let's let n be, I guess, 1. Is that where it started? Yeah. If n is 1, the first term here would be 1. If n is 2, we're going to have 1 over the square root of 2. Easy enough, 1 over the square root of 3. If we need more terms, we can generate them, but I'm going to come over here now. I want to see if these terms are less than or equal to, that's a question mark. So 1 over, let n be 1, that is 1/3. Next one is 1 over 2 plus the square root of 2, but you know, really there's no sense in going any further because just look at the comparison of the two first terms of each of the series. This is 1 and this is 1/3, and 1 is clearly not less than or equal to 1/3. So this fails, this resemblance fails. So what that tells us in this example is that I didn't choose a good series to compare it to. So we have to kind of backtrack and come up with a plan B and kind of think of, okay, well, what's another series that I could compare this to, and start all over. All right, well, since this one failed, if you want to make a note to yourself, fails, fine, plan B, or erase it, that's fine too. Okay, I'm going to come over here, see if I can come up with another series to compare it to. Well, although it's not real obvious, this is one that would take a little more work to think about. Okay, we're going to look at the harmonic series. Okay, so the comparison that I'm going to now choose is I'm going to say that this resembles, this is my plan B, even though not as clear as this resemblance. Okay, I'm going to think about 1 over n. Okay, so this is a divergent P series as well. So you might be thinking, well, that's not going to really help. Well, okay, this is one to kind of keep in the back of your mind, 1 over n as a comparison. Okay, so if this diverges, again, we're going to take the same route. We're going to say, okay, well, this one right here, if it diverges, we want this one to be the smaller one and the given series to be the larger one. Okay, so once again, we have a comparison, a resemblance of a divergent P series. So let's try another approach. Let's see if that's the case, then 1 over n, if that series diverges, then it must be the smaller series, so I'll call that a sub n, again, like the previous example, but maybe we'll make some progress. Okay, let's let a sub n be 1 over n. So if it diverges, then let's let this be b sub n, the larger series. Okay, so we'll do some term-by-term comparison. So is a sub n, the smaller series, 1 over n, is it less than or equal to, it's a question mark, 1 over 2 plus square root of n? Okay, so let's just generate some terms. If n is 1, then we have 1. N is 2, it's a half. Ooh, this is easy. A third, a fourth, etc. are these terms less than or equal to when we compare them to what we get over here? So this is 1 over 03. This is not looking good again. But sometimes some of these series are kind of tricky, and you've got to just generate a few terms, and we can qualify the convergence. Okay. Okay, so let's see what n is 1, now n is 2, so this is 1 over 2 plus square root of 2. Okay, the next one is going to be 1 over 2 plus square root of 3. Okay, and watch what happens here. 1 over, and when n is 4, 2 plus 2. Which is interesting because when you look at this term, 1/4, and how it compares to this term, it's the same. Okay, so that might tell us that we might want to generate a few more. You might be thinking, well, how would I know how many to generate? Well, this is one of those special cases. You don't really see this that often. What you do see is ones that are more straightforward, like example 1 and the next 2 examples that we're going to do. I just want to kind of throw this one at you guys. It is in the textbook. It is the example in there. And it's more one that you would kind of look at and investigate when you take this course at a university. Okay, so let's look at 5. So this would become 1/5. The next term will generate a few more, 1/6, 1/7, etc. So coming back here, this is term 1, 2, 3, 4. I got to put in a 5 here. So 2 plus square root of 5. Okay, this right down I'm going to wrap down. This is going to be 1 over 2 plus square root of 6. 1 over 2 plus square root of 7. So let's kind of pause here with these terms and compare them again. I probably should have wrapped this one down here. 1 over 2 plus the square root of 5. Well, the square root of 5, let's think about that. The square root of 5 is 2.23. So if I added 2.23 to 2, that's going to be a number less than a sum less than 5. So if this denominator is smaller than this denominator, then the value of this fraction is going to be larger. Okay, and you can take the time to compare them if you want. I know that's a lot right there to think about and compare. Let's look at this term compared to 1/6. Well, the square root of 6, if we were to calculate that, is 2.4 plus 2. So that's 4, a little over 4 here as a denominator, and so 1 over that number, okay, is going to be larger than 1/6. Okay, this right here, this fraction, if you were to figure it out, okay, is going to be larger than this fraction, 1/7. So it appears that when we do term-by-term comparison for the first 4 terms anyway, okay, this doesn't hold true. But after the 4th term, then we do know that this series is going to be greater than this series right here. So that's kind of how we can qualify it. Okay, so what we're going to say at this point is, okay, therefore, by the DCT, this series right here, n equals 1 to infinity of 1 over 2 plus the square root of n diverges like the one it resembles, but only when n is greater than or equal to 4. And I could say or equal to because in the actual test itself, we have less than or equal to. So I know that one's kind of strange. It doesn't come up often, but it's kind of interesting to note that based on the patterns of the term-by-term comparison, that at some point this series right here will be larger than the series it resembles. So maybe on the back of your notes, since you've got some blank there on the back of your notes, we're going to do 2 more examples in the next video, and they'll be a little more straightforward than this.